Let us solve the differential equation x dx equals 1 minus x squared secant y dy as a Bernoulli's differential equation. So the first thing that we have to do is to reduce it into a standard form, either this form right here, the first standard form dy dx plus p of x y equals q of x y raised to the power of n, or dx uh, over dy plus p of y x equals q of y x raised to the power of n. So to decide whether it should be the first standard form or the second standard form is to look at our given. So look at the expressions beside dx and dy. And here we can see that the expression sa dx na side is simpler compared to dy. Then we can say that it should be the second form. So dapat si dx ang nasa ibabaw. So we can reduce the equation into this form by first dividing both sides of the equation by x dy. So dividing both sides of the equation by x dy, we get dx dy equals 1 over x minus x secant of y. And then we follow this pattern. So it should be that uh, the second term here is p of y. So it's a function of y. And then we have x here. So it means that it's this term right here. So we can transfer this to the left side. Rewriting that, we have dy dx plus secant y x equals 1 over x. And then we can determine now which one is our p of y, which term is p of y, which term is q of y, and which term or which constant right there is n. So first we have p of y. So p of y is secant y. And q of y, if you can see here on the right side, we have 1 over x, but 1 over x can be written as, we can change this as x raised to the power of negative 1. So the right side is only a function of x. I mean, that's just x raised to the power of n, which means that q of y there is just the imaginary number 1. That's an imaginary number 1 there. And so our n is the exponent of x here, which is negative 1. So listing that, our p of y is secant y, q of y is equal to 1, and the value of n is negative 1. So after determining those three, then we can now solve for the integrating factor. So the integrating factor v is equal to e to the power of the integral of 1 minus n p of y dy. And substituting, that's e to the power of 1 minus negative 1 is 2, and p of y is secant y dy. So that's e to the power of 2. The integral of secant y is ln of secant y plus tangent of y. And so v therefore is equal to secant y plus tangent y quantity squared. So now that we have the integrating factor, we can now solve for the general solution. So for the general solution, our formula is vx raised to the power of 1 minus n equals 1 minus n integral of v q of y dy plus c. So substituting, our v is secant y plus tangent y quantity squared, and x raised to the power of 1 minus negative 1, so that's x squared, is equal to 1 minus negative 1 is 2 integral of secant y plus tangent y quantity squared, and our q of y is just 1, so we directly write dy plus c. So this is not yet integrable. We don't have a formula for this, so this binomial has to be expanded. Raising that to the power of 2, that gives us secant squared y plus 2 secant y tangent y plus tangent squared y dy plus c. So secant squared y is already integrable. 2 secant y tangent y is also integrable. But tangent squared y is not integrable, so we have to express this in terms of secant squared y. And from the Pythagorean identity, tangent squared y is equal to secant squared y minus 1. So expressing that or writing that as in terms of secant, so that would be 2 secant y tangent y plus secant squared y minus 1 dy plus c. So that's 2 integral of 2 secant squared y plus 2 secant y tangent y minus 1 dy plus c. So we can now integrate. That's 2 times 2 tangent y, that is our integral for secant squared y, and our integral for secant y tangent y. So that's plus 2 secant y, and the integral here of 1 is y plus c. So that's equal to x squared times secant y plus tangent y quantity squared. And so that is our general solution for our given differential equation.